Hello. Hey. Wow, a lot of people in the room. Thanks for being here. It's a super pleasure on my side to be here and attending the first edition of B-Sides. So I'm also happy that you have B-Sides here in Prague. So this talk is about industrial machines. I work for Trend Micro Research, and over the last 5 years, we look into this aspect because it's new. It's not been researched so far, and there is a wide surface of vulnerabilities and problems. I'm also president and co-founder of NoHat. It's a hackish conference similar to this one that we run in Italy in October. It's in English, so you're all welcome to participate. It's almost free entrance, so it's very easy and relaxed. So if you want to come over, just contact me and I will put you in a VIP line and we can network even outside of Prague. Cool. So why we're talking of industrial machines is because we have seen a huge revolution over the last decades. So you can see machines have been introduced already many years ago, but they were just pieces of that's machine, right? Like a piece of metal. While lately, there was a push on so-called smart machine. Someone can also say industrial IoT. So similar as you have in your home building, where you have like a smart TV or a smart refrigerator, anything should be smart. Here is a kind of similar situation. So actually, at the European level, there is a push for selling more and more of this machine. So if you have a company and you're going to buy a machine for producing anything, if you buy a smart machine, which is compliant with so-called Industry 4.0, usually you get a special discount or tax reduction. So that's why most of the people go with those machines that are connected. And this is cool, right? So there are a lot of functionalities because they can easily get integrated into the so-called shop floor. So where you have IT and OT that converge at the same time. So those machines that are connected either via wireless or proprietary radio protocols, as well as traditional TCP/IP, normally tend to be connected to the cloud, for example, for management. They connected to the database to know what is produced. So it's pretty useful, right? So if you have a huge factory, you want to know like what gets produced, or you want to interact with a machine remotely to change the configuration and change the pieces that are produced. So of course, there are some benefits of this integration of operational environments. So what is in orange here. And the traditional IT infrastructure. But, with functionalities, usually the problems comes, especially when the code that runs on those machines might not be the most recent code, but there might be legacy code. So this is the setup in which we did the research, and here I'm going to give you two short examples of previous work we have done on the topic. And if you are interested, you can find more on reference. And then we will dig deeper into so-called CNC machines. So machines used for manufacturing plants everywhere. So let me start with protocol gateways. So these are devices used to connect OT network with IT networks. Gateways like, for example, the router you have at home to connect to the internet, or the fiber or the ADSL router. But this one are used to convert OT protocols like Modbus, Profibus. There are a lot of like protocols specific to OT networks, legacy protocol, often serial bus, to TCP/IP. And these are essential part of your deployment because you can basically bring a legacy machine that was connecting only via serial into your TCP/IP network. So we look into these devices in the past. And we found a few interesting things I want to summarize here quickly before moving forward with the rest of the presentation. So normally a gateway is installed, as you can see here, in the middle of the screen, this device here. And what it does, I was saying, is basically translate all of this, which is what's called field network, so the OT network, into the traffic that comes from the TCP/IP network. So you can have a database, you can have an engineering workstation, HMI, which is the graphical user interface used to control what the production is doing. And this gentleman here does the conversion. Often you also have so-called ICS firewalls. So these one are very critical component because they make sure that the communication from the green line to the red line makes sense. So you can, for example, specifying rules that says, okay, I want to pull data out of a motor to know what's going on. But, if I'm not admin, I don't want basically to mess up. So to be able to write something of a motor, for example, change the speed of a motor, because this one might create a problem, right? It might basically burn the machine completely, or you might stop the production. So the SES firewall is the element that implement basically the policy for the operational environment. So problems here we found here, it's just one of the many in this work, that if you specify an incorrect length in the packet doesn't really get translated correctly, get basically copy over. So you can see here the bytes are always the same, they get copy over. But what changed here is that the mapping here, you see function code 4, it becomes function code 0F. So what means is that an attacker that generates a read request from the historian down to the OT environment, it actually translate that request into a write request. So a read input register, so a request for reading values out of these devices, get translated into a write multiple coil. So this one would allow the attacker to bypass firewall and to write, as I was saying, on the OT network, a bunch of malicious things. So this is one of the many problems. If you are interested in this topic, just give a read of the paper. It's like 70 pages paper. It was also a presentation we made at Black Hat, and there are some interesting findings here. But network like those one are not only connected via TCP/IP, they can also be connected over proprietary radio protocols. That's also an interesting thing here. There are more and more machines that are operated remotely via so-called controllers. So controllers can be like this. So you can have very simple controllers that basically allow you to move the machine right, left, up, down, or controller that use joysticks. So even now in follow-up research, we look into, okay, what's bad with those things, right? So what happened, we bought some of them. We went for the most prevalent one that are sold in different countries. This is one of the most used one. So as you can see here, there is a transmitter, which is this one, and the receiver unit. So the receiver unit get installed on the machine, and the transmitter is used by the operator to control the machine. So here is a different type of research. So on the previous one, we mainly work with fuzzer to find vulnerabilities into the protocol gateways. Here, instead, we work at hardware level. So what we did, we extract the firmware of the device. We look into how the modulation of a radio protocol is done. So I'm not sure how many of you have experience with software-defined radios, but this research go exactly in that direction. So the goal here was to reverse engineer the radio protocol of these devices to know if there were vulnerabilities. So in this specific case, here, for example, we decoupled the chipset on the board. Is a Texas Instrument CI, you can read there, 1120. So from there, you can try to guess which kind of modulation schemas are used. Based on that, then you can do the decoding, go from analog to digital, and then you can try to reverse engineer the payload. And here are basically what we did. So at the end of all of this, me and my colleague here, we went for some real-world testing. So we developed a tool that implement a malicious radio transmission system. So here you have, for example, my laptop with a bunch of software-defined radios, which are this device that you connect on the Ethernet device, on the USB port, and allow you to generate radio packets. And we went out to different facilities to test wherever you could possibly hijack certain machineries. And I have a small video here I want to show you. So let me see if it works. Yes. So here we went into a construction site. So this is a colleague of mine in the car with a laptop. This is me holding. So this is the legitimate transmitter here that I have here, that you use basically to control the crane. As you can see here in the video, I'm not touching the controller, but what you will see here is that my colleague from the car is basically able to move the crane while I'm basically, you see. So these are the sort of things you could do, right? As you can see, the impact of this is super severe. It can be this. This is another construction site. Here as well, that's my laptop with a software-defined radio attached here to the laptop. The legitimate transmitter here, nobody's touching it. So I run the attack, and you will see basically that the crane is basically moving up without doing nothing. Here is another one. Here you see? Here we generate the signal. This is crafted by the attacker. This is pretty huge. It's an overhead crane. Here again. So in this research we test not sure if there are statistics here, but if I recall correctly, it was something like 7 vendors, and they were all vulnerable to the same problem. So you can see here there are general problems with all these technologies, and this brings me to the core of my presentation, which is on CNC machines. So after having looked at how this machine communicate, both on the wires, on the network, and with radio protocols, then we went deeper into understanding fundamental problems of manufacturing machines. So these machines are largely used in the industrial world, and they encompass a wide diversity of terms. So there are drillers for drilling holes, there are letter machine, mills, grinders, 3D printers. I'm not sure how many of you had a 3D printer at home, but 3D printer are CNC machines as well, the small one. And these machines are very complex. Like this one is a machine which is installed in the Polytechnic of Milan. It's a local university in Milan. And it costs something like 250,000 euros, to give you an idea. And this one has a precision of 0.0001 millimeter. So 10 at -5. So what happens is that when the machine moves, it can move up to 0.0001 millimeter. So to give you basically the idea of the precision on how this machine operates, and is used for crafting very small, like metal gears, for example, that you use then in the automotive industry. Of course, there are tons of these machines, and as you can understand, these are critical asset, right, for all the productions globally. Very interesting things here is that you have a controller, which is this one here, and the controller is often the same across multiple machines. In fact, here, so the clicker has stopped working again. Wow. In fact, here we have a very complex supply chain. So take, for example, this machine I showed you before. So who's going to develop the machine? it may develop its own controller, which often is not the case, or it might go ask to an NC manufacturer, so basically the guy that developed the controller, to provide a controller. In fact, there are a lot of manufacturer of CNC machines. So there is a CNC machine for doing anything, basically. But there are not many vendors of controllers. So that's interesting things. It's like to say, okay, cool, like there are many Linux distribution out there. Red Hat, CentOS, Ubuntu. But the core operating system, which is Linux, is just one, right? So the kernel is always the same. So here it's kind of similar. So the supply chain consists of the simulator, the controller itself, which is basically the kernel here. Then there is the machine manufacturer, which has actually developed a machine based on the controller, the reseller, the integrator, and the end user. And all of this is very complex. As you can see here, there might be a bunch of problems all around the supply chain. So for this research, we decided to focus on the side at the controller. Why? Because if there are problems on the controller itself, all the supply chain get impacted by those vulnerabilities. Like to say, if you have a vulnerability in the kernel of an operating system, like let's say Linux, all the different flavor and variants of a Linux distribution will have a problem. It's the same things we have seen like last week with this new library that got a nice backdoor implant in the library. Basically, all the software using the library then are affected. Something similar. So what we did here, we consider 4 representative vendors of 4 different countries to make basically the study general, right? To be able to apply the study worldwide. We consider a controller from US, controller from Japan, one from Germany, and another one from Japan. So these vendors are probably the largest vendor on the market. As you can see here, are vendors that have been established, if you take Heidenheim, more than 100 years ago. So, it's not a new one on the market. They are very large companies, like having more than $1 billion revenue and thousands of employees. And so what we did, we work with both simulators and real-world machine for the experiments. Of course, we start with the simulator first because you don't want to break a machine. And then you go down to the machine. So the simulator, just for curiosity, come in 2 flavors. So there are software simulator that runs as a virtual machine. So you can just run it on your computer and test the virtual machine. There are other simulators instead that are physical. So they are basically like the device that you connect to the machine, but the peripheral are virtualized. All right, so how our research approach looks like. So we use an approach which is the same for all the vendors to make sure that we have a fair comparison of the potential problems that we could identify. So we did an initial scraping with general vulnerability assessment scanner, like Nessus, and there are many, just to get rid of very common vulnerabilities that we are not much interested about. So the focus is not on, okay, cool, it runs Linux and Linux has a bug. Okay, we know it. It's more like which kind of technology is domain specific, so specific to the CNC machine and might have problem. That's why we then move into investigating domain specific technology, so technologies that are specific to this domain. As you can see here, there are a lot of technologies that I was not aware of when we started the research, but these are technologies that are kind of common in, like for example, OPC UA is widely used, MT Connect is widely used, but all in this specific domain. And no one before looked at this. So if you're interested to work in OT security, there are a lot of like technology very specific. It's similar to the automotive domain. In car security, for example, is the same thing. So like there are a lot of specific domain. And this is what really the juicy part is. Then we did threat analysis to understand, okay, what could go wrong here, right? And then we developed a POC code that we tested on simulator and as well as on the real world machine. And then we work with CISA, which is a cybersecurity agency in the United States that help us to get in contact with the vendor. which is not easy, right? So we are not, if you find the bug like in, let's say, whatever, like Google or Microsoft, they have a bug bounty program, they have like security officer, they have like people that know about security. So you have a person you're talking to that understand what your problem here is. Here it's not really the same thing. So and I'm going to discuss that later. So it was very helpful, to have someone that allow us to talk to the vendor about the problem. So what are the general problem we have found? Legacy software, so similar to as a protocol gateways I showed you before, or even the radio protocols I showed you before. So there are a lot of, in all this OT space, often you deal with legacy software. So that's one problem. Second problem, you don't have much of mitigations. Like if you have a bug on software running on Windows, Windows has a lot of mitigation functionality embedded in the kernel, like random stack, address randomization, or whatever. There are many technologies put in place to prevent easy exploitation. Here is not really the case. So usually a bug means a problem. All right, it's like an exploit and an impact. A lot of leakages. So these smart devices, as I was telling you before, they are open for connectivity. So they are open for sharing information. They are friendly with anyone, right? But in your mean to be friendly with anyone, you often provide way more information of what you should provide. We'll see example. Problem with authentication bypass. And the problem with access control poorly implemented. So let me give you an example here. So this is MT Connect. MT Connect is a nice standard. So all the vendors support MT Connect. It's a standard used for making the machine communicating each other. So if you have a machine of a certain vendor and a machine of another vendor, if you want these two machines to communicate, to be able to operate in a production line, you can use MT Connect. It's a standardized language based on XML. So here, as you can see here, XML, I'm pulling some data out of the machine. So like what the machine is doing, blah, 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 blah. So if you can spot this, it means that you're already expert in the domain. So this is the line of code that is currently executed on the machine. So this is in G code. G code is the programming language used here, and it's very similar to a programming language used for robots. So what you can do here, you can write a small script that pull this variable out. You can basically dump all the code that run on the machine. So you can see here it's super severe because if I am a company and I have a machine that produces a piece, and an attacker can dump the code, basically I can steal all the intellectual property of a company because I know what is produced, how it's produced, I can copy the piece, I can make the piece better. So you can see it's a huge damage. And we are not talking of the most complicated vulnerability exploitation chain here. It's basically like a Python crawler that connect to the daemon and dump basically that information from MT Connect. Okay, so this one was reported and fixed very rapidly in this case, thanks to the guy. So another big issue is the lack of resource access control. For example, on us, which is one of the vendors we look at, they provide a proprietary protocol, which is this one you can see on screen, where you can query, for example, for the serial number of the machine remotely. We can query the machine to know what is produced on the machine. You can query, that's very sensitive one, that's why I read. You can query for the configuration of the machine. You can say, okay, what's the value of variable 10,000. So variable 10,000 is like in a certain area of memory. You can query for the value at that specific address in memory. And you can also write a certain area in memory. You can see, okay, cool, yeah, you can write anywhere in memory what could go wrong. Well, a lot of things. Actually, by manual, they say, okay, you can use this E command, but only to write certain areas, so from 1 to whatever. Actually, it was not the case. So when we look at this, actually, you can write anywhere in in memory with a lot of problems. I had a video here I'm not going to show you because otherwise this presentation is going to take like 3 hours, but you can find the extended version online, or you can ask me, I can give you more detail. Whoop. All right. What happened here? Okay, we are here. No, we're not here. Okay, let me go down. Oh, we have done already a lot of slides. It's a very interesting area of research here because it's pretty trivial to find a lot of problems. So that's the impact here. So these are our 4 vendors, you can see here. These are all the different attacks we came up to that map to the different class of attacks. So you can, the first one is compromise, like RC, remote code execution of the machine. The second one is damage, like damage, for example, the piece you are producing, damaging the machine. Damage include damaging for the operator, right? So a safety risk for the operator that is operating the machine. Denial of service attacks of different form. Hijacking, like taking control of the production. And theft of information, like leak of information. As you can see here, the impact is huge. So pretty much all the vendors have a bunch of problems. I'm going to give you some example of attacks we came up with. So let me maybe start with this. Just a sec. What time I'm supposed to finish? 11, right? Okay, well, 10 minutes. All right. So let's start with this one. Here you have on the right side here the attacker console. This one in black. Here you have a camera on the machine. So this is the CNC machine which is under attack. So this is a real world machine we use for the experiment. And this one is the console. So this is what the operator view of the machine. As you can see here, the operator can see the name of the program that they get executed. This is the source code of the program. So these are information of the program, like the spindle, so the speed in which the tool is moving. Here the position of the axis. So this is a driller, so it has 3 X, Y, Z. That's the position in the space. And this one is the interesting part. So here tells you basically how the machine is compensating. So let me explain a bit of this. So basically when the machine makes holes, so the point of the driller get consumed. So when you start drilling, things are okay. After you do like 1,000 holes, the tool gets shorter and shorter because you are basically consuming the tool. So what the machine does, it automatically compensates that to make sure that it always drill at the same depth. Okay? So this is how it works. This one is automatically done by the machine. So here, the attack. So what we did, we developed a code that would instruct the machine to create a piece that is like this. So like a hole of 5.05 millimeter depth. So this is what our code should do. So what we do here, we remotely basically tamper with the memory of the machine, and we introduce an error. I'm not sure you can see here because it's a bit small. We introduce a compensation error of 0.25 millimeter, so a quarter of millimeter. So what the machine does, basically, it introduces a micro defect in how the piece is developed. You can see here, when we perform the attack, the machine runs with the same code, so we didn't actually change the code, right? But the machine introduced this compensational error of 0.25 millimeter. Of course, For those machines I showed before that can operate at 0.0001 millimeter, you can also introduce 0.001 millimeter of error. So that's nothing. It's not even visible. I can easily bypass QA and in the company. So what the result of this is that if you do this sort of attack on a company gets out with a lot of pieces that may have defect. So think about the company that produce brakes for cars. So if you introduce a defect like this and you go to the market, then you can have a major issue, right? Because you need to recall the pieces back, and this is a huge problem for the company because you're going to lose a lot of money for recalling all the defective pieces. In terms of images, can be a problem because, if you do such attack and the reputation of a company probably would go down, right? So this shows how easy it is to remotely hijack a machine to introduce an error. We also did a similar experiment here. I'm going to show you. So for this, I'm going to show you how an attacker can actually damage the machine itself. So what we did, we use a 3D printer. We print this is the tool of the driller in plastic. You can see here, that's a plastic point we put into the machine here. And then we did the attack again. But in this case, instead of having a compensation factor of only 0.25 millimeter, we went for 10 centimeter. So at that point, the machine does not even understand that 10 centimeter is huge. So what it does, it basically, when it starts drilling, it compensates, it go down 10 centimeter into the metal piece, and it basically crush completely the plastic point. So this is, of course, is an experiment, but usually when you're drilling, for example, aluminium, you need a point which is harder than the aluminium itself. So in that case, you go for titanium, so points that cost easily like 15K, like 50,000 euros, 1 point, just because they're made with titanium. So you can see this sort of attack can damage the machine easily, right? So this is another example. This one goes back to what I was showing before with MT Connect. So here again, we have the attacker machine here on the right side. This is a POC. That's the machine that got attacked. As you can see here, this is another vendor. It has a different user interface, but basically it's the same stuff. So here you can see what the machine is doing. Here you can see the coordinates. Here you can see the code. So this is what the operator sees on the machine. So in this attack, the attacker, as I was saying before, remotely pull out the information from MT Connect. As you can see here, all these different points is because it's basically pull information out. As soon as he find a new instruction, you have a V here. So you can see at the end, you can basically remotely recover the source code of a program. And this is even more severe because when you dump the code here is interpreted. So, it's not compiled. And this is the same for CNC machine as well as industrial robots. So it's not a compiled code. It's like a scripting language, as you can see here. So if you are an attacker, you don't even need to reverse engineering. Basically the program, because it's super visible here. And this brings you to the next attack, which is this one I'm going to show you here. So as you can see here in the code here, you have a variable called K, which is VC1. That means K take input from a general variable called 1. And as I was showing before, since you can write to certain memory address in memory, you can alter that value. So if you have a machine that is drilling 2 holes because this value holds variable 2, if you are an attacker, you can remotely connect to the machine, change that value in memory, and at that point the machine will start drilling 5 holes. So this is the experiment we did here, and showed how a criminal can hijack the production and basically take control of the machine without changing the source code of the machine, can influence the machine in doing something different from what you're supposed to do. So this is also super severe because in a production line, you're producing pieces, an attacker can basically hijack the production and change what gets produced. You can even go further. So this is another example from, this is another machine. So here the machine is executing a code called 1000 with the source code here. So what the attacker does, it can download the program, change the program, for example, add this comment here, re-upload the command, and the machine at the next execution automatically pull the new code and start running that one. So it's also super severe. It's the writing of the program executed on the machine. This is another example. You can reset a so-called advanced management tool. So this is something similar to the compensation problem I showed you before. So here is basically a system in which allow you to do regular processing. So if you have like a program, a line that you produce pieces under pieces constantly, you need to change tools when they are wasted out. So you compensate, then the tool it's wasted out, you throw it away, the machine pick up a new one, continue to work. When it's wasted out, pick a new one. So it's called, here you can see the list of tools that are picked by the machine to be able to continue the production. So what happened here, there is a counter that counts how many holes the machine has done. So in this case, on this experiment, you see we have like the first tool is exhausted because he has drilled already 14 holes. So we are now working with a second tool, which is tool number 10. So what the attacker does, it can reset tool number 10. So what means that when machine is producing and start drilling with tool number 10, the attacker does, you know what? Reset the counter for tool number 10. So what the machine does, continue to use tool number 10 over and over and over. So at that point, you are basically, either you are creating a problem, which you are damaging the piece under production, or you're even damaging the machine completely because you start drilling with a point which is exhausted and you continue to drill and you might crash basically the machine against the piece you are producing with an impact on the cost of production. This is cool. So this is another machine. It's us. It's a US vendor. Actually, for those that are passionate of Formula One, I love Ferrari because I'm from Italy. Haas has his own like a Formula One car. Actually, they start from Formula One and then they went into CNC machines. This is what I learned. So this is a NAS machine, and you can see here there is this nice button called the feed hold. Feed hold. So what is this? It's a bit like emergency stop of a machine. So when the machine is doing something bad, you basically push this button. It's basically like if you're driving the car, right, and you have your brake. So if something happens, you just brake things. So it's like emergency stop. So here, again, by tampering a certain area of memory, you can disable this button. So it's super severe because it's like if you're driving a car and someone remotely connect to your car and disable the brake. So while you're driving, you have the first curve, you brake doesn't work and you crash. So here it's the same. And the machine even tell you the feed hold is suppressed. So when you do the attack and the victim, the operator press the button, the machine said, you know what? I'm suppressed. So I'm not going to stop. I continue the production. In this example, instead, is how this is the operator, which is producing something on a real world machine. Here it's how you can start monitoring the machine remotely. So you can dump information like the name of the machine, the serial number of the machine, the type of controller which is controlling the machine, which program is at the moment under execution. Here it's not running, here it's running. Here the line that is currently executed on the machine of a program. Here the number of pieces. You can see the counter here that go from 148 to 149. So this shows how an attacker can dump anything. Like he can know which machines are installed on a certain factory, which programs are executed on the machines, how many pieces are produced by each machine, and this is like game over. This is another example where you can trigger fake fake alarms, so-called software alarms. So machines support alarm which is physical, like there is a lack of oil on the machine, so there is a problem, as well as software alarm similar to interrupt in operating system. And this is an example where an attacker can trigger this software alarm remotely. At that point, the machine just pop up alarm and it stop. And at that point, the operator should go on the machine to debug what's happened and restart the machine from operating. And this is super severe because you can easily cause a denial of service attack. Finally, you can also ransom those machines. So this is an example where we compromise a machine, we metasploit, and we manage basically to screen lock, the user interface of the operator asking for a ransom. That's also an example of denial of service attack. So with all of this, I want to say that industrial facilities are cool because they are deployed more and more with smart devices that often have remote-based functionalities, which could be like a wire, traditional TCP/IP functionalities, or as we've seen in the beginning of the talk, based on radio protocols. The problem with all of those functionality applied to a world which I think is not ready for dealing with all these challenges, in that it wider the surface, the attack surface, and it open the possibility for a bunch of remote vectors. So us as researcher in security, we are responsible of conducting this sort of research to show that there are problems and to identify those problems before criminals can abuse them. That's our responsibility. And for that reason, we spent months going into a responsible disclosure process with a vendor. It took us I think something like 4 months to have, I'm not saying all of these problems fixed, but a large majority. And this responsible disclosure, it turned into a training. So we often had to educate them on the problem of having certain functionalities. But this is, at the end, why we do research. So to help the vendor into moving to a safer environment. And I want to encourage all of you to look into this area of research because it's just the point of the iceberg, this one. So there are more and more functionalities we didn't investigate from lack of time and we leave for future work that will for sure offer plenty of interesting research possibilities. So with this I conclude. These are my contacts, so feel free to connect with me over Twitter. Let's keep it under this name or online, and I will be happy to have a few questions let me see if time permit. Maybe, I don't know, just one question, if someone has one. Let me see. Yes.
Hi. Thank you for the presentation. It's very good research. You've been doing this for a while now, right? Talking with vendors and doing this disclosure and training. Did they mention anything like to any of these attacks being seen on the wild? Like maybe, hey, now that you're telling me we have these malfunctions, is this being actively exploited? Okay,
the theft of information, yes. So there are like cases of malware that arrive on a computer that is connected to the OT network, and this is basically the malware dump information from the machine. So it's both cases have been observed a lot, yes, as well as ransomware. It's very easy to ransom and block those machines. Yeah. Cool, I guess we are out of time. I will be here all the day, and for sure tonight I heard there is a great social event. So more than happy to have a beer with you and continue the discussion. Thank you.